Hey everyone, and welcome to this explainer on the Medical Physics Coding and Learning Hub. I am so thrilled you're tuning in. Today we're diving into one of the absolute most powerful open source tools in our entire field, and that's Pylinac. Now look, if you have little to no Python programming experience, just take a deep breath, it's totally fine. We're going to take this step by step together, and I promise you, it's going to be a really fun journey. Let's take a quick look at our roadmap for today's explainer. We're going to cover what is Pylinac, exploring GitHub, reading the documentation, installing with pip, running a Picket Fence QA example, and finally, some clinical best practices. Alrighty, jumping right into section 1. What exactly is Pylinac? So, at its core, this is an open-source Python library built specifically for us, therapy and diagnostic medical physicists. The huge takeaway here is that Pylinac completely automates the tedious manual analysis of imaging and performance metrics. It gives you a suite of TG142 quality assurance tools that pull data right from your Linac and CT simulator images. It calculates things like your modulation transfer function, or MTF, contrast and ROI metrics, and then bundles the whole shebang into these really solid professional PDF reports. It even has automatic phantom registration. So yeah, your phantom setup on the couch doesn't even have to be perfectly aligned for it to work. How cool is that? And to really put its efficiency into perspective, just think of the number 10. Most of these incredibly complex QA scripts can actually be executed with less than 10 lines of code. It is an absolute game changer for saving time. Okay, let's move on to section 2, exploring the GitHub repository. GitHub is essentially where developers build and share tools like this, and we're going to pull back the curtain on how it actually works. When you go to github.com/jrkerns/Pylinac, you're looking at the repository. You can just think of this as the master folder for the entire project. It holds all the files, the complete version history of the software, the actual Pylinac source code, and a docs folder where the manual is kept. Now, GitHub has a lot of developer jargon, but translating it is actually pretty easy. The README is really just the front page with some basic instructions to get you started. Releases are the official, stable versions of the code that are totally safe to use in your clinic. Issues is simply a tracker where you can report bugs or just ask questions. And pull requests, those are just submissions from users who want to contribute their own improvements to the code. It just goes to show how collaborative and transparent open source medical physics really can be. Section 3, reading the documentation. So while GitHub is where the code lives, the Read the Docs page is your actual user manual. Honestly, a well-documented project is a physicist's best friend, and you'll find everything you need right here. It's got installation instructions, incredibly detailed step-by-step user guides for specific QA tests like TG51 or Starshot, conceptual code examples to show you exactly how to structure your scripts, and a complete API reference. That API reference acts kind of like a massive dictionary of all the available functions if you ever want to get into the really advanced stuff. Let's hit section 4, installing with pip. Now it's time to actually assemble this thing, and don't panic, it's unbelievably fast. To get Pylinac onto your computer, literally all you do is open up your terminal or command prompt and type one simple command, pip install Pylinac. That uses the Python package manager to just instantly download and install the whole library for you. Easy, right? All right, section 5, the Picket Fence Q&A example. Now, for the really fun part, applying this clinically. You might be wondering, why even bother automating your Picket Fence QA? I mean, physicists regularly check MLC positioning with a picket fence pattern anyway, right? Well, why just eyeball a film visually when you can quantify the exact leaf positions digitally and with pinpoint accuracy? Let's see how this actually improves your clinical workflow. Pylinac's algorithm takes care of all the heavy lifting for you. It automatically loads up your EPID DICOM images, finds all the MLC peaks, and calculates the errors of every single leaf relative to the picket. It then spits out these super clear pass, warn, or fail visual overlays. And honestly, the coolest part, it automatically accounts for specific source-to-image distances, off-axis panel translations, and even EPID sag. The conceptual flow of the code is incredibly straightforward. It's basically 4 steps. Step 1, you just import the tool into your script. Step 2, you load your DICOM image file. Step 3, you hit it with the analyze command. And finally, step 4, you tell it to plot the data and generate your PDF report. That is literally it. When you're looking at that generated PDF, you're going to want to pay really close attention to a couple of vital metrics. The median error gives you the general baseline error calculated across all of the leaves. Meanwhile, the maximum leaf error is going to pinpoint the absolute worst performing individual leaf in the entire delivery. If you keep an eye on these alongside the error histogram, you're going to be able to spot systemic Pylinac drifts way early, long before they turn into real clinical headaches. And that brings us to Section 6, Clinical Best Practices. Before you go and completely replace your manual routine with Pylinac, we really need to talk about safety checks. You absolutely must follow these guidelines. Always verify your EPID panel orientation and translation. Double-check that the pass and warn tolerance values you put in your script actually match your specific clinic's guidelines. Validate your new results in parallel with whatever QA software you're already using first. And honestly, most importantly, never blindly trust a text result that just says pass. You have to visually review those image overlays to make sure the algorithm actually identified the pickets correctly. Look, if you get stuck on some syntax or documentation while you're learning, having an AI tool as a study buddy is a great idea. But you have to remember this. AI is an assistant, not a replacement for your clinical judgment. It simply cannot replace your hard-earned expertise as a medical physicist. So with less than 10 lines of code standing between you and fully automated PDF reports, I want to leave you with one final thought to chew on as we wrap up this explainer on the Medical Physics Coding and Learning Hub. What routine QA task are you going to automate next? The possibilities here are seriously endless. Thanks so much for hanging out with me today, and keep on learning.